Okay, so are we settled? So good morning. First Sunday of the month, and it's time for chai and wine. Before I formally introduce today's speaker, let me announce the upcoming session. Upcoming session will be on third Sunday of this month, so that is 17th of August. It will happen at Ruparel College. It will be given by Professor Aniket Sule from HBCSE, and it is about Olympiads. So you must be aware that India will be hosting the Astronomy Olympiad in a week's time. So it will be about that. So now that brings me to introduce today's speaker. Today's speaker is Mr. Jay Deshmukh. By profession, he is a condensed matter physicist. To be specific, he works on quantum computers. But today what he is going to discuss is something that is very close to his heart, music and the physics, or the physics behind the music. Okay. So he did his master's from BSMS from IIT Kanpur, and currently he is pursuing his doctoral work at TIFR. So along with being a physicist, he is also an avid footballer and music enthusiast, and play guitar as well, right?
Yes.
And perhaps we'll get to hear something? Well, I look forward to hearing your guitar. Okay. So with this, all yours.
Thanks for Lars. Is my feed coming? Okay. Okay. Good morning, everyone. Thanks for coming here on this Sunday morning. And today I'm going to try and convince you that the sounds that we find pleasant, which we call music, have some rooting in physics or the nature that we see around us. So to start off, I'd like to do a small activity. I'll play two tunes, and you have to tell me which one you sound more pleasing. Okay? And bonus points if you recognize the tune. It's yeah. Okay, it's a smart audience. Here's the next tune. Yes, so which one was better?
First one.
Okay, so we all universally agree that for some reason the first tune was better. And I always thought about this, that why does everyone agree that the same music sounds nice? Like, what is about that particular sound that we like? So let's try and answer these questions today. So I believe that the reason we found the first tune kind of pleasing to the ear is because it was constructed from the notes of the major scale. So if you've come from a Western music background, you may have heard of the major scale and with notes that I've identified as these letters. And if you come from an Indian music background, then you may have heard of Sa Re Ga Ma Pa. I hope everyone has heard of Sa Re Ga Ma Pa. And the point is that you separate one octave into 12 equal parts, and there are 12 notes which occupy an octave. So just to demonstrate what an octave is, Ninad, can you tell us what an octave is?
Okay, so in both Western and Eastern music,
Yeah.
an octave is a set of 7 notes with the 8th one being the first, same as the first one, and that's it. That's why it's an octave. And there is a definite relation between sequential notes.
Yeah, so just maybe you can show the Sa and the higher Sa.
Right. So I've been trained for some time in Indian classical music.
So this is Ninad, he's also a physicist from TIFR and my very good friend.
So if I set this as the Sa, so if given this Sa, if I have to take the third note, Sa Re Ga.
Yeah. Okay.
Right?
Yes.
Ah.
So Maybe if you show sa and the higher sa.
Yeah, then with respect to this, the fifth note, the pa will be sa, pa, and then the octave, the
Yes.
eighth note will be sa, sa.
Okay, thanks, Nat. So this octave is chopped up into 12 parts, and 12 notes occupy this much of the frequency space. And this seems to be common across cultures. And it's an interesting question, like why these notes, why 12, and how are they related to each other? There's a particular nomenclature to refer to these 12 notes. So if we call the first note as the root note, then its relation to the other notes is defined by something called an interval. So for example, what Ninaj first sang, the sa and the ga, in Western music, it's called a major third interval. Similarly, the sa and the pa, it's called a major fifth interval, sorry, a perfect fifth interval. And the sa and the higher sa, it's called a perfect octave. So we'll come back to these intervals and we'll see why they are deeply rooted in physics. Now, before we answer the question as to why these specific notes sound good, let's answer a more fundamental question, like what is sound itself? So basically, sound is just the information of objects moving or particular motion at different points in space. And because these objects are performing some motion, they create a disturbance in the medium around us. So for example, when you close the door, the air molecules around the door, they sense the motion of the door, and that disturbance travels across the medium. And what you sense is actually the disturbance that is traveling via this medium. Sure. When it is minimized. Okay. Yeah. So for example, when a speaker plays a tune, what's actually happening is that there's a membrane on the speaker which is performing some particular motion depending on what the music is. And then because of that, the air molecules close to the speaker's membrane are disturbed. And these disturbances, they travel in the form of these pressure differences in the medium that occupies the room. And finally, it reaches your ear. So what your ear actually detects is the small variations in pressure at the space point that is where the ear is. And to just visualize this in a more abstract way, you can think of this graph representing the air pressure. So in this cartoon, you can see that the air molecules are more densely packed or not so densely packed, and that is represented by this sort of a wave, where the peaks represent points of high pressure, and the crests, the dips represent the points of low pressure. Okay. Am I audible on YouTube? Yeah. Okay. Okay. So basically, sound is disturbances that are traveling via the medium that occupies the room. And our ears detect such excitations because of some very, quite amazing machinery that exists, but I'm not an expert on that, so we're not going to talk about that. What we are going to talk about is physics. So just to set up some vocabulary before we proceed, I kept referring to these disturbances as waves. So waves are just periodic changes in any quantity. So in our case, it was pressure. So if I think of this as a snapshot of the pressure varying, the length the pressure takes to again come back to the same value is defined as the wavelength. And if I now stand at one point and I measure the pressure, and I measure in how many times the pressure varies and comes back to the same point in a particular second, that's called the frequency. So that is the wavelength and the frequency of the wave. And they are related by this particular relation where the wavelength times the frequency is the speed at which the sound travels. And this is fixed for a particular medium. So all you need to keep in mind is that wavelength and frequency are inversely related. So the larger the wavelength of a sound, the lower the frequency. And the reason we are interested in this term frequency and amplitude is because they are related to how we perceive the sound. So for example, if the pressure variations are very wild, so if you're varying from very high pressure to very low pressure, you perceive that sound to be loud. So now loudness is something that we understand, and that is related to the amplitude of the wave. Similarly, if the pressure varies very quickly, like within a second it's going up and down very fast, so that means the frequency is high, and how we perceive it is as a high pitch. So when the pressure changes very quickly, the pitch of the sound is high. When it changes slowly, the pitch is low. Now, these are all very idealized curves. How, let's say, this is an example of the sound produced when a balloon bursts. So the actual variations in pressure are very weird and very strange. They're not these nice waves. Now, it turns out that there is something hidden in how this pressure varies, and that determines whether the sounds that we perceive is musical or not musical. Now, here is an example of how the pressure variation may look when certain musical instruments are played. And can you notice anything about how the pressure is varying? Yeah, there is some sense of periodicity which you can see. And so in the concert hall, whenever these instruments are playing, they are going to generate these disturbances around them. And finally, what you hear is going to be a combination of all of these disturbances that you perceive where you're sitting. And in this added waveform, it's not so obvious whether something is repeating or not. But, I think if I play all of these instruments individually, as opposed to if I play them all together, we would agree that we'd find the combined waveform the most musical. So it's not as obvious, but there is some hint here that there is some sense of periodicity which is hidden in what the music is. Okay. Now, we are going to take a bit of a detour from musical instruments to these objects called strings and pipes. And we are interested in them because most of the instruments that we typically listen to are based on these geometries. And there's going to be something hidden in the physics of how these objects resonate, and that's going to tell us a bit about how music emerges from them. Okay. So let's consider a guitar. So this is a string which is held tightly, and it is, the condition is that it's kept stationary at both the ends. So now when I pluck it, the string can't move in an arbitrary way. It's going to be restricted to a particular class of motion, which preserves this condition that the end points are stationary. Now, if you think of these, what I'm going to call the harmonics of the string, so the string can move in a very, like in a very complicated way, but it can always be decomposed in these fundamental motions. And the actual motion of the string is going to be some combination of these. So let's look at the first motion in which the entire string is moving together. And there's a node at exactly in the middle of the string. And this is going to be the fundamental note that the string plays. So this motion is going to disturb the air around it in a particular way, and you're going to perceive that vibration as a particular pitch in your ear. Similarly, here is the second mode in which now you're going to fit two half wavelengths. So now, if you think about, if we go back to our definition of the wavelength, it was when in a particular wave, the pressure changes and it comes back to its original point. So if you look at the second harmonic, here, the string is going up all the way down and then again back to its original place. So in this case, the wavelength of the sound is actually equal to the length of the string. And similarly, we can see that as the harmonics increase, their wavelengths are actually 2L, 2L by 2, 2L by 3, 2L by 4, which is basically L by 2, and so on. And so the frequencies associated with each of these motions will actually be, so if the first mode resonates with the frequency F, the higher modes will have a frequency 2F, 3F, and so on. So just to demonstrate it, this is one note. And now if I forcefully ask the middle of the string to not resonate, so basically I'm dampening the frequency of the first mode because I'm not allowing it to resonate like this. And similarly, if I now put my finger at 1/3 of the length, you can hear all of these different pitches, and these are the harmonics which the strings are generating, and I'm able to distill them by adding these boundary conditions by hand. Okay, so this series of frequencies, F, 2F, 3F, 4F, and so on, is something that I will call, or everyone calls, the harmonic series. And the actual movement of the string, as I already said, is going to be a combination of all of these allowed modes. So when you play a string on the guitar, you're not actually hearing one note, you're hearing the notes which are being generated by all of these individual motions. Now, let's go to this very nice website that I found, and let's try to listen to all of these frequencies individually. So the first sound will correspond to some frequency F defined at some arbitrary number, and then this will have the sequence F, 2F, 3F, and so on. So this is F. This is 2F. This is 3F. 4F. Do these notes sound familiar? So Ninad had already shown us that what is this interval? It's an octave. Ninad sang this as sa and pa. So, and so on. This is actually the perfect fourth interval. And if anyone has played an instrument, you must have.
Keyboard.
Which instrument do you play?
Piano, electric.
Okay. Do you know the major chord?
Yeah, I know. C, E, G.
Yes.
Yes.
Do you know how to sing the notes of a major chord by any chance?
No, I don't know how to sing.
Okay.
I know how to.
Can you sing it for me, please? Sorry?
I can only do it with the piano.
Okay. Can you sing, let's say? You can come on the stage. Yeah, you can come on the stage. What's your name?
Manu.
Manu. Okay, so Manu is going to sing the G major chord for us.
C, E, G, C, E, G.
Perfect.
C, E, G.
Yes. And now this sound. That's kind of remarkable, right? That just from the physics of strings, you're somehow able to recover the notes in which harmony is deeply rooted in. And now if we continue this process and so if we continue this process, you will actually start recovering all of the notes that occupy the octave. And we were interested in the 12 notes originally, in which you have divided one octave. And then you can do this process where you keep playing these frequencies and then you map it back to the first octave by dividing it by 2, because every time you divide the frequency by 2, you're reducing it by an octave. And soon enough, you will almost, there are some subtleties here, but you can almost recover the notes that we use to create the music around us. The subtlety is that, now let's look at the top half of this image. So these are actually the 12 notes which you will generate via the process that I just described. So for example, if this is your C, then E will be 16 by 15 times the frequency of C. Sorry, D. This will be C sharp, and then D will be 9/8, and so on. So for example, C and E will have a frequency ratio of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5/4 of the frequency ratio. And C and G will have 1, 2, 3, 4, 5, 6, 7, 8, the 3 by 2 the frequency of C. And the problem with tuning an instrument like this is that, let's say I tune it perfectly to a particular key, and in that case, the major third interval with my first note as the root will have a ratio 1.25. But now if I want to choose, want to play an interval where this note is my root note, and I play its major third, so their frequency ratio will actually be 8 by 5 by 5 by 4, which is 1.28, which is quite different from 1.25. And so this will be a little restrictive in the sense if you tune your instrument to a particular key, the intervals will only sound good if that the root note is one particular note. And over time, culturally, I think people just wanted to play around by changing keys within a song. And so they invented something called the equal temperament tuning, in which you divide your octave into 12 equal parts. And the frequency ratio of any two consecutive notes is the same. So now when you tune the instrument with this condition, then it wouldn't matter from where you start. If you go 12 keys up from wherever you started, you will always end up one octave high. And that's because any two frequencies will be related by the 12th root of 2. And it's a very cute mathematical property that all of the powers of the 12th root of 2, they happen to be close by to all of these nice ratios. And because of the finite resolution of our ear, and because culturally perhaps we have evolved to find these pleasing as well, this works just fine for us, and that's why the piano sounds nice. So I'm not an expert in this part, so this is all I know. But I find this quite interesting for two reasons. One is that all of the notes that we found pleasing, which were generated from the harmonic series. Second of all of the frequency ratios are these nice small ratios. You don't have a ratio like 53 by 51 or something like that. They're all these nice small numbers. And then we happen to find a tuning in which the ratios are actually irrational, because if you've heard of rational and irrational numbers, the 12th root of 2 is an irrational number. But all of the powers of that irrational number, they are close enough to all of these 12. And you can now tune an instrument in a way which is now more flexible.
So, do we have like some understanding of why these slightly uneven ratios sound peculiar? Because they match.
So there, if you see in frequency, they'll not be too far away. Just an absolute frequency. So, so this is some sort of a compromise that you're not sounding exactly in tune in any key, but the flexibility is that you won't. So if you tune yourself perfectly in the just intonation and you tune in C, and then if you want to play suddenly in, let's say, G, I don't know, it'll sound a lot more detuned than your compromise.
No, about just intonation actually.
Okay.
It's not an exact solution of frequency.
Uh-huh.
So when we talk about the exact multiplication,
Uh-huh.
you are going one octave up by multiplying the frequency by 2.
So that is true in just intonation.
So, but when you split a single octave into notes, it's not a very even, like the just intonations are not very even distributed.
Yes, yes.
So, do we like have a scientific understanding why those harmonics are really?
So actually, I was going to reverse the question. Like perhaps we find those pleasing because these sounds are the structure sounds that you find in nature. I mean, I'm not a.
What is the CD communicated with harmonic kind of instrument?
Oh, so.
Just repeat the question.
Okay, so the question is, what does this C, D, E, F indicate? So these are just labels for the notes uh, that, uh, uh, that, that the piano plays. So for example, if you play this note, if you press this key, the sound that comes out is mapped to a particular symbol that people use to communicate what to play.
Why is Saregama has been designed like that? Why is so much of a
Why it has been designed that way?
when we say Saregama, it includes all the notes.
Uh-huh.
So why does it happen? What is from the point of swing side?
Uh-huh.
How does it relate? The Saregama relates to all the notes.
What I'm trying to convey is that perhaps the Saregama pi is emerged because the harmonic series exists in the physics of the strings. And yeah, I don't know who invented Saregama pi and why they did it, but we can only hypothesize that this is the reason we happen to found those notes pleasing. Because for some reason they seem to be rooted in how a string moves and what are the allowed frequencies.
You said it earlier, when you have those ratios,
Uh-huh.
that helps you maintain that periodicity of the notes, right? So if it's 16 by 50 means that you will repeat
Yes.
exactly at
Uh-huh.
a certain point of time.
Uh-huh.
And it's those kind of periodic things which tend to sound
Yes. Yes.
pleasing. Because
Yeah.
you have a repetition.
Yeah. So yeah, that's a better answer to your question. So essentially what Vijay said is that if the ratios of the frequencies have, so let's say I have something oscillating with frequency f and something oscillating with frequency 2f, then they're going to repeat a lot often than something with a ratio which is a larger number. So perhaps you have to weight lesser to find repetition, and it's easier to perceive a pattern when you play two frequencies which have a nice ratio between them.
So my question, I think it's because something in our brain. Like each frequency, the way it sounds like, and it has an effect in our brain. That's why we assume sa, re, gamma, pa, da, ni, sa for each frequency. The way it oscillates, that we make, like we assume those frequencies to be sa, re, gamma, pa, da, ni, sa, C, D, E, F, G, A, B, C. Because I observed it while I was like playing the keyboard a few days ago.
You notice that there's something, just something
Yes,
very
something in my
intrinsic.
brain that's telling me yes, this should be C.
Yeah. So
Nature is evolved.
yes. Yeah. So yeah, I don't have a good answer to why, but I can only motivate as to, maybe there is an aspect of this which is relevant to why we now find it so natural to like these notes.
I can maybe try to, so I can tell you what my Guruji told me about music, is that no one decided that this should be the scale and this is what we should call a given scale. This is not a prescriptive science. What he said is that there are sounds in nature, including so many classical songs we talk about how the poem sings. So all the sounds that we heard in the nature, we try to organize them, and this is the pattern that we found. So rather than being prescriptive, it's a descriptive thing. The sound that we hear.
Yeah.
I just want to add something to what you just said. It's a little bit more than that. I think maybe that's what Jay is trying to connect. Like there is a reason, mathematical reason, why those are the sounds we heard in nature.
Yeah.
Because the things which can produce sounds have to follow the laws of physics. There is a math behind it.
Exactly.
That is the reason why we heard those tones, and this description tells you how the math describes that these 12 notes have a certain property which makes it pleasing, so it forms that scale. It's true that we heard from nature and tried to organize it, but there's an underlying reason why that happened.
Yeah. Okay. Now I want to relate harmony with rhythm. So let's go back and think of the sounds that we just established that they sound good together. So we saw that they have simple frequency ratios, and I didn't really talk about this part, but it's also true that if they have those ratios, then they'll have overtones which will be overlapping, and that's why they'll sound more stable. But this is only if you already have background. It's not important for this talk. So I want to make this claim that rhythm is essentially harmony slowed down a lot, or harmony is rhythm that is sped up. So let's listen to this. You perceive rhythm here? It's kind of pleasing. It's very pleasing to me. And the reason that I chose, now let me walk you through how I constructed this rhythm. Okay. Yeah. So basically there are 3 independent beats which are playing. So the first one, the first one is this. It's just 4 beats in a particular section. The second beat which is playing is, so it's 5 beats. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And the third one is 6 beats. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And when all played together, this is how they sound. And if we go back, to our harmonics, the 4th, the 5th, and the 6th harmonics, they have this frequency ratio with respect to fundamental, which is 4 times, 5 times, and 6 times. And essentially, I'm claiming that the beat that I just played is related to what it would sound like if these notes are played together. And here's a small, I tried to create this demo myself, but I could not. So here's a small video that we can watch.
Let me demonstrate. Listen to this funny little rhythm for a moment. What does it have to do with harmony, with, let's say, a major triad? Well, it's actually kind of the same thing. Let's speed it up. Pretty cool, right?
So I didn't know that a few months back, and I thought that was amazing. Okay, so I just want to summarize the part that we have seen till now before we move on to the next part of the talk. This part or? Yeah, okay, thanks. So first we discussed that sound is just a vibration that travels in the air, and it just contains the information of motion that is happening at some other point in space. Musical sounds are structured. They show some sort of periodicity and order. We haven't really spoken a lot about this. We will visit this soon. But you did see this when I showed you the waveforms of the different instruments. Most instruments are based on strings and pipes, and then we didn't really talk about pipes, but that's homework. You can go home and derive the harmonic series from the physics of pipes. And all instruments actually sound a little bit different because they have their own harmonic fingerprints. So they sound a little different because of how much each overtone is present. That dictates, along with a few other things, so I can play the same note in a guitar versus a flute, but you can tell which one is played with a guitar or a flute, and that's because of they have these unique harmonic fingerprints. And from the harmonic series, we got the intervals of the music, which we are very familiar with. We talked about how over time we transitioned from just intonation to equal temperament, and finally that harmony and rhythm are very intimately related.
I wanted to ask, like, similar to instruments which all have their own fingerprint, sort of.
Mm-hmm.
Does everybody's voice have a different waveform? Which makes the voice different.
Yes, that's true, because everyone's shape of the mouth cavity or or the vocal cords, they'll all be different. They'll have slightly different properties, and that's actually the reason why you and I sound different, perhaps. So that's very interesting.
So if you took the waveform of, let's say, me speaking this sentence, and you record, and you just took the waveform itself and replicated it somewhere else, would it be the exact same as what I'm saying right now?
Probably not, because there are some other things which also dictate which is related to more of the transient behavior of the sound. But I do think you can, play around with how your voice sounds a lot by changing what harmonic content it has. But probably you can't manipulate it to the extent that you want to. And for that, you probably need something more. But yeah, that's a very good point. Okay, so let's go back to vibrating strings. So as I kept saying, the string's motion will be some combination of all of the fundamental modes that we, or the other harmonic, or the harmonics that we talked about. These are the harmonics, these are the motions that are allowed, and finally, how the string moves will be some combination of these, and therefore the sound that it produces will have a pitch which corresponds to almost all of these motions. So, let's say this is my fundamental tone, and this is the first harmonic, and this is the second harmonic. I've reduced the amplitude a little bit for aesthetic purposes. And when we add these, we get this sort of a motion, which doesn't look, as simple. It looks a little complicated, but, there's some structure. And now you can kind of keep on adding these harmonics, and you see that you get this very, it's very periodic, but it's not a simple looking function. And it is but because we have constructed this ourselves, that it consists of just pure sine waves. But just by adding these pure sine waves, you have managed to make something more complicated. Now, what if we wanted to ask the inverse question? Like, let's say I told you that the string moves like this. Can you tell me what are the motions, the simpler motions that constitute this motion? And it turns out that you can answer this question. And how many of you have heard of this term called Fourier transforms? Okay, so that's almost what the Fourier transform does. It takes an input and it tells you at what frequency how much content is present. Now, if you look at this graph, you see that I told you that for aesthetic purposes, I added the other waveforms at a lower amplitude, and okay, you haven't seen how I did it, but there is a certain box that you can put this function in, and it outputs this graph in which it tells you should add a sine wave at this frequency with this much amplitude, and a sine wave at this frequency with this much amplitude, and so on, to recover this function. Again, just to revisit, periodic functions can be expressed as sum of pure sine waves. Given a function, you can decompose it into constituent pure sines. And this is called this is actually called the Fourier series. Fourier transform is mathematically a little different, but we don't care about that right now. And what I'm going to now claim is that we can use this to distinguish musical sounds from noise. Now, I'm going to try a demo, and I hope it works. So this is a window which will actually give us the Fourier transform of what we play. So now so here also, you can see that when I play a particular note, you see these very distinct peaks at particular frequencies. And now, can you see the frequency written on the top left with hertz? So this peak corresponds to 131 hertz. This corresponds to almost 262. This corresponds to almost thrice that number. You can do the math, and so on. So you can see that what you expect from the harmonic series is kind of present in this instrument. Well, okay, this is not the most honest because I played something that is synthesized. I can also play it with the guitar. It's just a little bit more complicated with the mic. Now I want to show you how perhaps a noisy sound or a sound that you would not associate with a musical instrument would look like. Check. Dept. Give me a moment. Now I can also play my guitar. You see that the frequency content of the guitar also has peaks. Now if it's possible, can you all make a lot of noise? Did you see what happened? Yeah, actually, let's go again. 3, 2, 1. Do you see any structure here?
No.
So what we see is that the Fourier transform can actually distinguish. Where did it go? It's fine. Yeah, it's fine. It can distinguish musical sounds. So a musical sound had this sort of a structure in frequency, whereas something with a lot of noise had a very broad frequency content. So in fact, this is how you can actually mathematically define noise as something which has a very broad, not very structured frequency content. Right. So, that's the name of a mathematician, Joseph Fourier, and he came up with this technique to, let's say you were given a particular function in time, any sort of a motion, you can decompose it into its constituent sine waves. And what I'm claiming here, that this tool is being used to take in the sound of the guitar, and it is giving us the peaks at which the frequencies of the sound exist. And therefore, a sound produced from the guitar has a lot of a lot of content at these particular frequencies, a lot of harmonic content at these frequencies, whereas something that is noisy doesn't have any structure and frequency. It's basically broad. Uh-huh. Yes. Yes, it does. Okay, I think Vijay has a ready-made answer.
So noise cancelling headphones do not distinguish between noise and music. Anything external to you will get cancelled. But it does, better job of maybe certain frequencies for certain depending on the noise.
Yeah.
It's job, so I guess it's really I guess it's a misnomer. It should not be called sound noise cancelling.
Yeah.
In the context of your talk.
Yes.
It should be just called sound cancelling.
Yes.
We just assume that everything outside of us when we want peace and quiet could be music also.
Okay. So just because we have talked about Fourier transforms, it's actually a lot more, you can find this in almost every field in science. So not just in sound, but also in solving differential equations and also, signal processing and data compression. It's an entire world in itself. And it's a very, very general tool. What I want to say here is that we started off from the physics of strings and we started off from music, and we kind of arrived at this very abstract mathematical concept of Fourier transforms, but it's still deeply rooted in the physics of these things which resonate. Now, I just want to kind of end with a thought, which was similar to the question that you asked. That now, given a piece of music, like I flashed, the waves generated by individual instruments, and what you hear is a combination of those. Now, given a piece of music, can we decompose it into its constituent instruments with the help of Fourier transforms?
I have done that. Like for example, like once I think I don't know, there was some Bengali song. My father asked me to play it on the keyboard, and I played it just by hearing it.
Wow. So were you doing Fourier transforms in your head?
It's difficult to say, but yeah, probably.
I see. So it turns out that the Fourier transform can't do this because, as we saw, when I play the same note on two instruments, how much the overtones exist is different, but they still occur at the same frequency. So if you have content at the same frequency, that's not something that a Fourier transform can, distinguish between. So it feels like a very human task to listen to a song and then distinguish what's happening in the vocals, what's happening in the guitar. And yeah. Now, I was quite amazed at this, that this is something that I thought, a skill that I would pick up after a lot of practice is now just available to us. So I just wanted to show you this software. And I'm going to play a song. Given a complete mix of all songs, this software is able to distill all the individual instruments because it's doing something which is beyond Fourier transforms. And it is.
Can it take out the vocals completely?
Yes. So now you have a in-house karaoke machine. Actually, I'm not playing the vocals here at all because I'm not sure what the lyrics are like. Yeah, so this task feels too human, but it turns out that neural networks can be trained to do exactly this. So essentially, they represent some complicated function, just like Fourier transforms represented a black box. Now this is a different black box, which is not Fourier transforms, but something that we don't understand. But it can take a musical piece inside it, and it can output stems of the different individual instruments. And yeah, I thought that was a very, I mean, I still don't believe that this can happen, but it does. Yes. Yes, so the thing is you have a lot of data like this available because you record instruments separately. Yes. Yeah. So when you train it, you can give it that label that, let's say you give it the full song and you give it the individual stems, and then you tell that this is the drum stem, this is the guitar stem, this is the violin stem. And then once it trains on this data, then you can, it probably also takes apart the stems, but it also gets the label correct. Yeah. Uh-huh. Yes, different levels of, yes, but the frequency content will happen at the same. Yes, so where the frequency is occurring.
So the Fourier transform can say what are the frequencies for this particular instrument?
No, it can't. It can't because, the combined signal will have some, let's say, some amount of content at this frequency. But now after that, how much of this has come from this instrument and how much it has come from the other instrument, that it cannot distinguish. Yes.
So the question is, so an aspiring musician or a singer, he actually look at the Fourier transform of what he is doing, and it will help him improve music.
So, okay, it won't help you in the way that I described, that it won't tell you what is more musical versus not more musical, because I'm assuming if you're making music, you're already going to be using the notes of the chromatic scale. But a lot of the sound engineering, the mixing and the mastering is actually essentially this, that you want to tailor the frequency content of all the individual instruments that they don't overlap and clash with each other. So all of the mixing softwares, I don't know if you've used Logic or Ableton, essentially this is what is happening. When you tune the EQ, even in your car, you're essentially changing the frequency content of the sound that is being produced, and all of that has Fourier transforms hidden inside it. So you can definitely make your songs sound better by using Fourier transforms.
I think there is some software which will kind of evaluate how you start sounding what the original was. What is the match between the and the original?
That's actually something what he is saying.
Oh.
Can Fourier transform predict what I create?
So the started from ideas.
Oh. I haven't come across this, but sounds very interesting. Okay.
So this is that online.
Yeah.
Can AI or Fourier transform help predict whether my music will be likable, or it will be classified as noise?
It can definitely tell noise and not noise. That much I think Fourier transform can tell. After noise, likable, not likable, and yeah. I mean, I'm sure AI is better at that than Fourier transform, for sure.
So probably people have got different. Okay. So what I suggest is with this we'll stop the online part.
Yeah. So let me just summarize the slide.
Oh, I thought.
No. Just yeah. So basically, again, sounds are vibrations that travel through space. It needs to have a medium. That's how the disturbance in the medium travels to us. Musical sounds are structured. Now we saw this in a lot more glory, that there is periodicity and structure in the frequency content of musical sounds. From the harmonic series that we got from the physics of strings, we generated the intervals of music, the octaves, the fifths, and everything. Harmony and rhythm are intimately related. Fourier transforms reveal hidden patterns. In our context, hidden patterns in frequency. And we saw a cool example of what can happen beyond Fourier transforms using artificial intelligence. Thank you.
we'll close the online part, and just to remind you, the next session will be on 17th of August. It's titled as Bridging Minds Through Stars, and it's about the International Olympiad on Astronomy and Astrophysics that will be held in Mumbai in a week's time. Okay, so we'll stop the.
Yeah.
And now speaker is available for your questions, so please feel free.
So I'll leave the meeting.